Welcome back to day 30 of SM219. Today, I'll be working through this worksheet on random variables, expected value, variance, and standard deviation. I'll assume that you've already gone through this worksheet, and so I'll just briefly summarize things and then answer some of the questions. A random variable is a measurement in an experiment, and in this first example, we show you how to compute the probability that that measurement is equal to 2 for a particular random variable. We also show you how to compute a particular number associated with a random variable called the expected value, or the mean, or sometimes the average value of the random variable. And it's computed using this formula here. The variance of the random variable is another number associated to the random variable. It's the expected value of the squared difference between the random variable and the expected value. And here's an example of how you compute that number. The variance has units equal to the units of x squared, and that makes it hard to interpret. So instead, we often take the square root of the variance and call that the standard deviation. The standard deviation tells us something about the spread of the possible values of our random variable, the standard deviation has units equal to the units of the variable, which makes it easier to interpret. In this first question, we're going to compute the expected value of the wait time for this bus. And so what we have to do is sum up the values of the expected variable. So for instance, 0 is one possible value, and we multiply it by the probability that the random variable takes the value 0, which in this case is 40%. And then 1 is a possible wait time, and it occurs 20% of the time. 2 occurs 30% of the time, and 4 occurs 10% of the time. And when you compute the expected value, you get that the expected wait time is 1.20 minutes, which is what we were hinting at when we said that the digits sum to 3. Yeah, so they do. Okay, let's compute the variance of this same random variable. And for this, you need to compute one of the possible values, like 0 is one of the possible values for the random variable. We subtract off e, and then we square that number, and we have to weight that number by the probability that the random variable takes the value 0. And then we do something very similar for each of the other possible values for the random variable. We take, for instance, 1 minus e squared, and we weight it by the probability that you get a 1, which is 20%. And then similarly, 2 minus e squared, and weight it by 30%. And then 4 minus e squared, and weight that by 10%. There we go. And oops, when you run it, you run into a problem. Let's just see where the error is occurring here. It's occurring right at the end. Oh, what's the problem here? I don't need this extra bracket. All right, the variance of the wait time is 1.56 minutes squared, and the sum of the first two digits, 1 and 5, actually is the third digit, 6. So we think maybe we got the correct answer. Okay, so set S to be the standard deviation of the wait time. Well, the standard deviation of the wait time is just the square root of the variance. Take the 1/2 power of V, and you get that the standard deviation of the wait time is 1.25 minutes, and the digits here do sum to 8, right? So that's good too. Okay, so the random variable that we showed you in example 1 and this other random variable that we just did now are both examples of discrete random variables. And discrete random variables come in families. There's These are important probabilistic models for uh, random variables. And there's many different kinds of families, and they all have different names and different parameters, and you need to kind of understand all of them if you want to be an expert in probability, but we don't really expect you to be an expert in probability. Really, here we just expect you to have some passing familiarity with families of discrete random variables. Maybe one of the most important is the binomial random variables, and those have two parameters, n and p. N is the number of times you conduct a certain experiment, the number of independent trials, and P is the probability of success for any of the trials. And the random variable takes value equal to the number of successes among your N trials. Okay, great. So for any probability distribution, like the binomial random variable, you can look up its probability mass function, and the height of the probability mass function gives the probability that the variable takes the value x. So it's essentially the probability function. And you can also look up an important related notion called the cumulative distribution function, the CDF. And the height of the CDF function is the probability that the variable takes the value x or a lower value. Okay. And you can look up the PMF, the CDF, the mean, and the variance, and many other properties of the binomial distribution on the Wikipedia page for binomial distributions. Here it is. And the fourth question here, it says, look up the mean of the binomial distribution, also look up the variance, and find the expected value and variance of the random variable, which has n equal to 20 and p equal 0.5. Okay, so we go to the binomial distribution, and there's a lot of text here, but fortunately here on the right, there's some summary stuff. Here's the binomial distribution. It takes two parameters, n, and they explain what the parameters are. That's the number of trials. And P is the success probability for each trial. And then they've got another parameter, which is often used, called Q, but you can see it's completely determined by P. It's 1 minus P. That's the failure probability for each trial. And then further down, you can find the probability mass function, and the mean, there it is, n times P, that's good. And also the variance, n times p times q. Aha. So let's go back to our notes. N is 20 in our case, because we were told n is 20, and p is 0.5. So we're, say, flipping a coin 20 times, and we're counting the number of heads, and the probability of getting a head is 1/2, and the probability of getting a tail here is 1/2. And the expected value is n times p. We got that from the web page, and the variance is n times p times q. There we go. The expected value is 10, and the variance is 5, and the variance should be half of the expected value in this case, and it is. Excellent. Okay. There's many other families of discrete distributions, and it's helpful to know a little bit about some of them. The hypergeometric distribution is one of them. It's kind of related to pulling red and blue balls out of a sack, and it's explained here. And the negative binomial distribution is another important distribution. It counts the total number of heads if you flip a coin with probability of heads equal to p until you flip your rth tail. So you keep flipping until you flip the rth tail. And one of the interesting things about the negative binomial distribution is that it can take infinitely many values, right? You could flip 0 heads and before you flip your rth tail. That would involve you flipping r tails in a row just at the beginning. Or you could flip 1 head before flipping the rth tail, or you could flip essentially any arbitrary number of heads until you flip your rth tail. So, the negative binomial distribution could take value 100 or 1,000 or 100,000, even if R is just 3. So it's kind of an interesting distribution in that regard. There's a super important distribution called the Poisson distribution, but we're going to leave that discussion until your homework assignment. Okay. So question 5 asks us to identify essentially which probability distribution governs a certain situation. So our ship will continue to function until it is hit by a total of 3 missiles. Each missile fired at my ship has probability 0.3 of hitting the ship. The number of missiles that miss my ship before it ceases to function is a random variable with which distribution. So that sounds like the negative binomial distribution. We need to know, in this case, a success should be a missile that misses my ship, right? Because I want to count the number of missiles that miss my ship, and I want to count the number of missiles that miss my ship before it ceases to function. And ceasing to function means 3 missiles hit my ship, and so that's 3 failures. So I'm going to count the number of successes, number of missiles missing my ship until 3 failures. So that tells me that I'm discriminating now between 3 and 4 here, negative binomial distributions, and P in the negative binomial distribution should be the probability of a success. A success is the things that we're counting, the number of missiles that miss my ship. So a success is a missile missing my ship. Each missile fired at my ship has probability 0.3 of hitting my ship, so it has probability of missing my ship 0.7. So here the correct answer is 4. The negative binomial distribution with P equal 0.7 and R equal 3. Okay, great.